Okay, continuing on with chapter 9 on rotation. This is part 4. Okay, so we're going to learn uh, more about spinning objects, and this time we're going to be able to relate angular variables like angular velocity to linear variables like linear velocity that we've talked about before. Okay, so first off, um, let's just make sure we understand the concept of arc lengths. All right, so if you're walking in a circle, you're walking along this black line here, right? The arc length is the distance in meters you have walked, right? So if you've only walked through this amount of angle, right, you haven't walked around the whole circle, you've only walked this far. So how far have you walked? Well, we're going to call that distance S, and that's the name for that is the arc length. Okay, and you can kind of tell the bigger the circle is, the further distance you're going to walk for the same angle, right? If this is a 10-meter circle, this S, and you walk through maybe 30 degrees or something, that angle, that distance isn't going to be very much. Whereas if this is a mile circumference circle, and this is again, you're walking through 30 degrees, this is going to be a much bigger distance, right? So the bigger the circle, the bigger R, the bigger the arc length, and you can also tell the bigger the angle you walk through, the bigger the arc length. So it turns out the equation that describes this arc length is this one down here. Now this is special because this equation is only true if we define our angle in radians. This equation does not work if we use degrees. So for some of the equations in this chapter, they are only going to work for you if you use radians. So that's why we generally want to always use radians in this chapter, just so you don't make a mistake of accidentally using degrees with an equation that doesn't work for degrees. Okay, so here's our equation. The arc length S, the distance in meters, is equal to the radius of the circle times the arc times the angular displacement, delta theta, in radians. Okay, so if I walk 3 radians, if this angle is delta theta is 3 radians, and the radius of a circle is 10 meters, then I've walked 10 meters times 3 radians tells me S is 30 meters. All right, so that's how I figure how far I've walked here. And you'll note the units don't seem to really make sense right now. R is the radius, that's in meters. The angle here, the angular displacement, is in radians. So I have meters times radians on this side, where S is arc length, that's only in meters. So it doesn't seem to make sense, meters and meters times radians. Well, it turns out radians aren't really a unit. They're really unitless. We like to keep radians around because it just helps us with converting from degrees to radians, things like that. So it's still useful to say, okay, this angle is 3 radians, but it turns out radians are unitless. Okay, and just to kind of further emphasize this point, here I have a different angle. Okay, so if I know the arc length and I know the radius of the circle, I could figure out the angle I've turned through in radians, just dividing S by R, dividing the arc length by the radius. Or if I know the angle I've turned through and I know the radius, I can figure out how far I've walked using S is equal to R theta. Okay. And as I said, it's still, even though radians is not really a unit, it's still really useful to just write rad. If it's 20 radians, just write 20 rad, and that helps you if you ever need to convert from radians to degrees or degrees to radians. It just helps you keep in mind this is an angle that you're using. Okay. And then just as a reminder, I think everybody is familiar with the circumference formula, right? How far is it to completely walk around a circle? The circumference of that circle is 2 pi times the radius of the circle, right? That's the distance in meters that you have to walk around this entire circle. Okay, it turns out this equation that you've all used before is just a special case of the arc length formula. Right? If you walk completely around a circle, you're walking through 2 pi radians. That's how big your angular displacement is. It's 2 pi. All right, so using our formula for arc lengths, r delta theta, in this case, the delta theta, if I walk all the way around, is just 2 pi radians. So I have the distance I've walked is the radius times 2 pi, which is exactly my circumference formula. All right, so you've used this equation before. Okay, so now our goal is to relate linear and angular velocity. Right, as this wheel is spinning, this turntable, the bug definitely has angular velocity, right? It's moving through some amount of angle every second, some number of radians per second, right? But it also has linear velocity, right? At any given moment, it's moving some distance and it's moving some number of meters per second. Yes, this velocity vector is continuously changing direction, right? The linear velocity of this object, but it does have linear velocity and angular velocity. So we want to be able to relate those two things. Since this linear velocity, is always changing direction, um, we know that, again, there must be some kind of acceleration affecting the bug. There must be some kind of radial acceleration, some acceleration towards the center of the circle, which is keeping this bug moving in a circle, which is changing this velocity vector. And we also can note that this velocity vector is always tangential to the path of the bug. If this dashed line is the path the bug takes as this wheel spins, um, and the bug is just sitting on the wheel moving around in this circle, at any given moment, the velocity vector is always tangential to the circle. Right? So when the bug is here, its velocity is in this direction. When the bug is here, in that moment, the bug is moving in this direction. So the linear velocity in meters per second is sometimes called tangential velocity when something's moving in a circle, but this is still just meters per second. Okay, and let's just think about what this bug is really doing. So every time it goes around one complete circle, how far is it traveling? It's traveling around one circumference, right? To go from here all the way around, how many meters is it actually traveling? We can use our circumference formula, 2 pi r, and if the bug is at a radius of 2 meters, 2 pi times 2 meters is 4 pi meters. So the circumference of the circle is 4 pi. And say it takes 1 second to complete that entire circle, well, we can just talk about speed in the traditional sense of how many meters are you moving every second. You're moving 4 pi meters per second. So that is our tangential or linear speed. This bug is moving at 4 pi meters per second. In the same time period, it also has angular speed, right? Meaning that it's going through some amount of angle in some period of time. And its one complete circle is 2 pi radians, so the angular speed is just 2 pi radians per second, right? So we want to be able to note both of these concepts and also convert between them. So in order to convert between them, let's see here, we can use our arc length formula. Okay, here's our arc length formula. As the bug moves through some angle delta theta, the distance it's traveling, s, is given by this formula, and linear speed is just how far you travel in a given period of time. And so this is how far you're traveling, s, some distance in meters, in some period of time, right? So this is our linear speed. And we have an equation for s. It's r delta theta. So I end up with this equation. And I just note that delta zeta over delta t is what omega is. This is our definition of angular velocity, a change in angle in time. So I can replace delta zeta divided by delta t with just an omega. So now I have a formula I can use that relates linear velocity v and angular velocity omega. V is equal to r omega. Okay, so that's really useful. In fact, you can already note that this bug and this bug will have the same angular velocity, the same omega, since this whole object is spinning with the same amount of angle every second. But the green bug is going to have more linear velocity, right, because it has a larger radius. The green bug is traveling a much further distance in the same amount of time, right? As this turntable turns, it takes the same amount of time for the green bug and the red bug to go around one complete circle. But the green bug is traveling much further, right? So that means it must have a larger linear speed or larger tangential speed, okay? But it has the same angular speed. And we can actually look at the simulation real quick. So I can, again, see if I can recreate that picture. I can put the bugs at 2 different points on this wheel, and I can start it spinning. Let's see, I'll give it maybe 40 degrees per second of angular velocity. So they both have exactly the same angular velocity. Every second, they're both moving through another 40 degrees, and you can kind of see both of them have the same angle at every moment. Okay, and I can actually draw on here the linear velocity, vector v, and you can see that this little bug, it's not traveling very far every second, so it has a small linear velocity or tangential velocity, where the green bug has a larger vector and it's traveling faster. Okay, so you can imagine holding hands with, let's say, 10 people and spinning in a circle. The person closest to the axis of rotation really isn't going to be moving at all. They're just going to be spinning around, with the person very far out the furthest person out on the edge of the circle is going to have to be running really, really fast to keep moving in that circle. Okay, and let's see, maybe I'll make the spin a little bit faster. And let's see, you can see at the moment the green bug has this big velocity vector, where the red bug doesn't have a velocity vector at all, right? Because it's not really going anywhere. It's not traveling any distance in a period of time. It has angular velocity, but doesn't have linear velocity. The green bug has linear velocity. It's going some distance every second, right? It's moving. If I put the red bug out here, let me try to get it on the line here. Now this bug has some linear velocity. It's smaller than this one because it's closer to our axis of rotation. Okay, and we can also do this with some graphs, which is useful to us. So let's see, I'm going to plot our angle, our angular velocity omega, and our velocity v. So in general, light green is going to be our ladybug, and dark green is going to be our beetle. And let's see, I will give the ladybug that position, I will give the beetle that position. I'm gonna, let's see, I'll put it in degrees just so we're consistent to what we had before. And let's see, I'll give it an angular velocity of 50 degrees per second. And you can see once again, the beetle has a larger vector here. You can see both the beetle and the ladybug have exactly the same angular velocity. It's 50 for both of them. But I can also note here, if I zoom in, that the ladybug and the beetle have different linear velocities. The ladybug is moving at 0.995 meters per second, where the beetle is moving much faster. It's moving at 2.673 meters per second. Okay, so, and you also know that the angle of both is the same at all times. I've got constant slope here corresponding to a constant angular velocity. Okay, so back to our presentation. So you can see we're going to now be able to relate linear and angular velocity, and in general, the further you are out on a spinning object, the faster you're going, right? The bigger my r, if every point of the object is the same angular speed, the further out I go, the bigger my linear velocity is going to be. Okay, and so if I have just some generic, weird-shaped object which is spinning about this point O, and I have this distance r, which is the distance from my axis of rotation to this atom, this piece of that spinning object, and this object is spinning with some angular velocity omega. At this moment, this little atom has some speed. It's moving tangentially to this circle in this moment, and that speed is given by v is equal to r omega. Okay, so you can always calculate the actual linear speed of a spinning object using that formula. And you'll note that the further out you go, the bigger the r, the bigger the v. Right? So if I pick point A and point B on this wheel, and the wheel is spinning with some angular velocity omega, point B is going to be moving at every moment with greater speed. Right? It's traveling further in the same amount of time. Okay, we can do the same trick with acceleration. As I noted before, as this turntable is spinning, there must be a force keeping this ladybug moving in a circle. There must be a force causing acceleration, which is moving that velocity vector, making that velocity vector change direction. All right, so that we've talked about before. That's our radial acceleration. And anything that's spinning is going to have that. That is the acceleration keeping this bug moving in a circle. Right, there's some friction between the turntable and the bug, which is applying a force which is keeping it on the turntable, keeping it moving in a circle. Right, but if I now spin this turntable and I increase the rate at which it's spinning, if I give it some angular acceleration, this ladybug is also going to have linear acceleration in this direction. If in this moment it has velocity in this direction, it's also going to, and it's also speeding up in that moment, it's also going to have acceleration in that direction too. Right? So we're going to give that acceleration the name tangential acceleration. Right? To understand the magnitude of that, we'll use the same formula we derived earlier that relates linear velocity and angular velocity, and let's just take the derivative of both sides. dv dt is just acceleration. d omega dt, that's just our instantaneous angular acceleration. So we can also always figure out this tangential angular acceleration using this formula, right? That if I know the angular acceleration alpha and I know the radius r, I can always figure out the tangential acceleration A of that ladybug. And you'll note once again that if I spin this turntable and I give it some angular acceleration alpha, both the beetle and the ladybug have to have the same angular acceleration because again they're both fixed, they're both at the same angle at every given moment. At every given moment they both have the same theta, the same omega, and the same alpha. So alpha is going to be the same for both of the bugs. But this bug out here, the green beetle, it has a bigger radius. That means it's going to have a bigger tangential acceleration. Okay. It also means that the force on that beetle is going to be bigger. The force of friction is making that beetle spin is going to be bigger. And that beetle is going to be more likely to fly off this turntable than this ladybug for that reason, because that force is bigger. Eventually you get beyond that static friction point, and the beetle will spin off the table. So, okay. So we now have actually two types of acceleration for a spinning object. So again, I have this weird shape object which is spinning. It has some angular velocity omega. At this moment, it has some velocity in the tangential direction, right? And then if I also am speeding up the rate at which this is spinning, so omega is getting bigger, I have angular acceleration. In addition to my radial acceleration that I always have no matter what, if I'm spinning, I also have this tangential acceleration because my velocity at that moment is also getting bigger. So I have acceleration in this direction and in this direction, so I have some kind of net acceleration in this direction. But we're always just going to break this up into components. One component is going to be this radial component of the acceleration that points along the radius towards the center of the circle, towards the axis of rotation, and this tangential acceleration, which is tangential to the circle. The tangential acceleration is given by the equation we just derived, right? A tan is equal to r alpha, and the radial acceleration we've seen before. We know how to calculate radial acceleration. It's v squared over r, right? That's something we saw in chapter 3, and we've used a few times in the class so far. We also have an equation for v. If we recall, we derived earlier that v is equal to r omega. So in our tangential acceleration formula, I can replace v with r omega. One of the r's cancels, and I can also write this in terms of angular velocity. So my radial acceleration is also equal to r omega squared. So if I'm spinning, I always have a radial, and if I'm spinning faster or slower, I have tangential acceleration, right? If I have alpha, if I have angular acceleration, I'm going to have tangential acceleration. Or if I have angular velocity, I'm going to have radial acceleration, right? Okay. So just a quick reminder as we finish up this section that this equation, our original arc length formula, is true only if this angle is measured in radians. And we use this equation to derive these other equations, which means if we want to use this equation, or this equation, we have to use radians. Okay, this formula works. This, if I turn this needle from here to here, it's turned to pi over 3 radians. What is this blue line? What is this distance? This distance is given by pi over 3 radians times r, using our arc length formula. That is the right answer in meters. The answer is not 60 r. We cannot use degrees here. Okay, and so all of these formulas are only true if we're using radians. So be careful with that. Now let's have a quick clicker question. Here I have just a typical bike where I have a front sprocket, which is very big, and a back sprocket, which is small, the rear sprocket. And as this thing is spinning, it's asking which of these has a bigger linear speed and which has a bigger angular speed. Okay, so take a moment and think about the answer. And when you have an answer, I won't tell you the answer yet, I'll give you a quick hint. Both of these sprockets must have the same linear velocity at the edge, right? So at this location and at this location, both of these sprockets must be moving with the same speed, right? The reason for that is this chain is a solid object. It can't stretch and it can't really compress, right? This is a solid metal chain. And so, this piece of the chain is moving at the same speed that this piece of the chain, which means that this piece of the gear here must be moving at the same linear speed as this piece of the gear here. So the velocity at each of these locations is the same, the linear velocity. And the second hint is that we have an equation that relates angular velocity and angular and linear velocity, or angular speed and linear speed. Okay, so hopefully with those hints you can think about your answer a little bit more. And when you're ready, on the next slide we show the answer. All right, so the answer here is D. Both of these sprockets have the same linear speed, but the front sprocket has a slower angular speed. All right, that has to be true. If both sprockets have the same v, same linear speed, but the front sprocket has a bigger r, it must have a smaller omega. Okay, so the front sprocket will be traveling at a smaller angular velocity. It'll be traveling a smaller amount of angle every second, but the edge of it is still moving at the same velocity as this one. Okay, so that's a nice quick little problem. Okay, so that's it for this section.